Hello student to the foundation of classical electrodynamics course. So today under module 2 we will have lecture 39 and today we will going to discuss the conductor and we will continue the discussion. So we have class number 39 today and we will going to continue the discussion on conductors. So we already mentioned in the last class that in conductor we have free electrons, and suppose this is a conducting sphere and all these free electrons or the charge will say accumulate. If I put some charge in the conductor, say plus q, so they will be residing on the surface, making the total field inside of the conductor equal to 0. Also whatever the field that one can expect just above the conductor. So, this is the conductor where all the say positive charge, induced charge is say residing on the surface like this, and just above the surface if I want to find out what is the electric field, then that value last day we calculated, it is sigma divided by epsilon 0 with unit vector n, where unit vector is along this direction which is perpendicular to the surface. Well, today we will try to understand few more interesting thing regarding the conductor. So, that is the induced charge. How the charge is induced I already mentioned, but today we will try to understand in a different aspects with different aspects. So, induced charge. So, suppose I have a conducting sphere here, say a sphere or cell, and I put a charge particle here outside. The charge particle q is outside. Now, since the free charge in the conductor can move around in such a way that it cancel off the field of the q inside the conductor. So, all the charge should reside on this. So, if say I put a plus q charge here, so this is a positive charge, all the negative charge will sit here this side and the positive charge will be here. So, this is the way the charge will be distributed over the conductor. So, here the point charge is outside the conductor. Right, and since all the free charge can move and they can arrange in such a way that they can cancel up the field inside, so that all the charge can be. So, whatever the charge here we have, the equal and opposite whatever the field we have here, equal and opposite field will be. So, one field will be here and another field will be like this. So, they will cancel each other. One is the external field and another is the induced field by this charge distribution. Now, the Now, the thing is, let us put the point charge inside this sphere. So, how I can do that? So, suppose I am having a sphere like this, and inside I am making a cavity like this. So, this is the cavity inside, and I place my point charge here, which is say plus q. So, then the question is, now the problem is the point charge is inside the cavity of the conductor. So, that is the situation we are having. We have a conductor, and inside that cavity we are having the point charge. Now, the field inside the cavity is not 0. That is the interesting thing, first we need to understand. So, the field inside the cavity is not 0. The field due to the charge within the cavity. So, what happened that, okay, now this is the thing we need to first understand, why it is not 0, and you can understand easily by just when we place a charge inside this cavity. So, there are two surfaces of this system, this conductor. One is the inner surface and another is the outer surface. So, all the negative charge will going to sit here in the over this negative surface, over this inner surface, all the negative charges will be this, whereas all the positive charge are going to sit here. Like this. So, now if I, so here the important thing is, here my E should not be 0, and using simply the Gauss's law, if I make a Gaussian surface here, you will find that these things. So, what is the, if I make a Gaussian surface here, then according to the Gauss's law, we have E dot ds inside the cavity that is total charge q enclosed divided by epsilon 0. So, if I have a sphere here with r, so then E and then the surface 4 pi r square, that quantity, let us omit this vector sign. Then the total charge inside is plus q divided by epsilon 0, where r belongs to the cavity. So, r is inside this cavity. Then E should be simply q divided by 4 pi epsilon 0, that is epsilon 0 r square, that is the field which is non-zero. that we understand. But the point is what happened here, I mean in this region. So, in this region again I need to draw a Gaussian surface. So, this will be my Gaussian surface now, because I want to find out the electric field inside the conductor, and already we know that inside the conductor there should not be any electric field, but here the situation is slightly different, because inside the cavity, inside the conductor we have a cavity, and that cavity contain a charge plus q. So, this is my Gaussian surface. So, this surface is my Gaussian surface. So, now again I am going to use the same law to find out what is going on there, and my law suggests that here I need to make this notation total, because it is inside the cavity and the total surface I need to calculate. So, here I will do the same thing, that the integration closed surface integration E dot ds will be, for this Gaussian surface, will be q enclosed divided by epsilon 0. Now, note here the q enclosed contain the plus q charge and also these induced negative charges, because you can see these induced negative charges and the plus q, both charges are there inside this Gaussian surface. So, I should write here 1 divided by epsilon 0, there will be two charge, one is simply plus q, that is already there in the cavity, plus another is the induced charge. Okay. And now, you can see that q induced is nothing but minus of q, right, because whatever the positive charge you place, the equal amount of negative charge should be here in this over this surface. So, that makes this quantity 0. So, eventually we have closed line integral E dot ds is simply equal to 0. That means that gives us that E is 0. This is where? Inside the conductor. Inside the conductor. But not the cavity. You should, inside the conductor means only this annular region, in this region. Okay. Now, a similar thing one may ask that, okay, I have a sphere here, and inside the sphere I am having a cavity like this, and again I have a point charge sitting plus q charge sitting inside this cavity. So, what should be the field at some point r? What is the field at some point r, where r is greater than the radius of this sphere, say a, or say big R. Big R is the radius of this sphere, but I want to find out what is the field outside. And the result, if I draw a Gaussian surface, again the distribution, if I look carefully, the distribution will be, the negative charge will be sitting here, and the positive charge will be over this, equal amount, it will be just distributed like this. And if I want to find out what is the electric field here, it will be like I am only having one charge q, because at this point it will going to ignore all the induced charge, because they are equal and opposite. So, as if only one charge is here and you just simply ignore what is happening here, and I should have a result like 4 pi epsilon 0 standard result r square with unit vector r if I put in vectorial form. So, that should be the field at the outside. So, three cases I just discussed. One is if there is a charge outside, what happened? So, there will be induced charge like this. If I put a charge inside the cavity, then what happened, that inside the cavity there will be a field, non-zero field, but in the annular region inside the conductor, we should have a non-zero, we should have a zero electric field. And another is far away. If I want to find out what is happening far away, even though I put a charge inside the the cavity of a conductor, then the result will be simply like this. Now, next I will discuss the charge distribution. So, next topic is the charge distribution. Charge distribution on the sphere, on the surface, not sphere, on the surface of a conductor. We mentioned that the charge will be distributed over the surface for a given conductor always, but the charge distribution may not be uniform. So, that is the point I try to make. Suppose I have a conductor with this kind of shape. This is a conductor, this is not a sphere, but a shape like this. I have a sharp edge here. So, in this kind of conductor, if the total charge is distributed, the charge will not going to be distributed with uniform, uniform. If I give a charge here, so it will not going to distribute uniformly. So, in this edge the charge will be distributed like this. There will be a very dense charge distribution one can expect in these sharp edges. Again there will be so here in this regime, the greater charge density one can expect, greater surface charge density. Greater surface charge density can be observed in this region. Here we have a plus sign. So, we can easily find it out that what happened. So, suppose I have a sphere here, two conducting sphere, one with radius R A and another is with radius R B when R A is greater than R B. So, this is two conductor, and this is say R A and the radius is say R B, where R B is less than R A. That is the condition. Now, I already draw a line here. So, let me just erase this part. Yeah. So, I already draw a line, that means I am just before joining these two conductor with a wire or something, I put a charge here. So, QA is amount of charge is given here and QB is a charge I just give to this conductor. So, now QA and QB charge will be distributed uniformly, and for the conducting sphere the potential, we know the potential for the conducting sphere is simply that we know that it is q divided by 4 pi epsilon 0 r, when r is less than r for a sphere, when r is the radius of that, and equal to q divided by 4 pi epsilon 0 small r when r is greater equal to r. So, that means in the inner region, for a conductor the potential is constant, and when we go outside the conductor then it reduces in the form of 1 by r. So, that means in our case we have phi a is simply the total amount of charge is given q a divided by 4 pi epsilon 0 and r a, and phi b for other conductor is q b divided by 4 pi epsilon 0 and r b. Now, I join these two conductor with a with a wire or something. By doing that, it become a equipotential. Now, this entire conductor become a single conductor with the condition that it is having a equipotential surface. So, the equipotential condition leads to, so equipotential condition leads to the condition leads to phi a equal to phi b. So, that means from this equation I can simply have q a divided by r a is equal to q b divided by r b. Now, the charge is distributed. So, I should have a surface over the surface. So, I should have a surface charge density sigma, and that is q divided by 4 pi r square in general. So, sigma a is simply q a divided by 4 pi r a square, and sigma b is q b divided by 4 pi r b square. So, this is q b. So, sigma a and sigma b we know, and also I have a condition here. So, if I just replace this q a with in the form of sigma, so I can simply have sigma a and then 4 pi r a square divided by r a is equal to sigma b 4 pi r b square divided by r b, or in other words sigma a divided by sigma b is simply r b divided by r a. So, from that we can understand that sigma is inversely proportional to r. So, in this case the charge will be distributed. So, that means here simply sigma b is greater than sigma a, as RA is greater than RP, because it is inversely related, right. This is the condition I get. So, that means we have a very, in this case you can see the radius of this curvature is smaller, and since the radius of this curvature is smaller, it is expected that the charge density will be higher compared to this region where the radius of this curvature is larger. So, if the radius is larger, the charge density over this region will be smaller, and if it is smaller, then the charge density will be larger. Now, the corresponding electric field, because in the surface it is distributed. So, I should also have a electric field associated with these things, which is along this direction. That should be the associated electric field E, and that again depends on sigma, right, because electric field, we know that electric field E is how much? It is sigma divided by epsilon 0, sigma divided by epsilon 0 with unit vector n. This is in the vectorial form. So, that means the electric field is proportional to sigma. So, the electric field will be also higher. So, that means if I want to find out the electric field for these two spheres, one is say E A and another is say E B, then E A. So, from here we can also write that E B is greater than E A. So, this is the condition I should have. So, yeah, this is the thing I actually wanted to cover in today's lecture. So, I just mentioned that how for a conductor, what are the properties of the conductor, few important properties, and how the charge is accumulated over the surface, how what should be the charge density, etc. This is not a very new thing, because most of the students should know, but I just recap in the context of this conductor. So, today I am going to stop here, because I do not have much time. In the next class, what we do that we try to understand some phase matching condition, or the matching boundary, not phase matching condition, rather I should say the boundary condition of the electric field, when the electric field is going from one medium to another medium, and in the interface if we have some kind of surface charge density, then how to deal with that, what should be the boundary condition of the electric field, different component of the electric field, that we will going to discuss. So, with that note, let me conclude here. Thank you very much for your attention, and see you in the next class.